Okay. So have you ever run into that problem where you need to know how many different people hit a website?
Oh, yeah.
Or maybe the number of unique IP addresses popping up in network logs?
Definitely. And your first instinct is just, wow, count them.
Exactly. I'll just list them out. But then you look at the sheer volume of data and it's suddenly not so simple.
No, it feels like trying to count, I don't know, grains of sand on a beach. It really shows up a big challenge with large data sets. How do you estimate the unique items, the cardinality, without using up all your memory?
Because those old school methods, keeping a list of everything you've seen, they just fall over with big data.
They really do. They just don't scale.
And that brings us to what we're diving into today. There's a really neat technique called HyperLogLog. Sounds kind of space age, right?
It does, but it's very real. It's a probabilistic data structure, basically a smart way to solve this exact problem.
So for you listening, maybe you're, wrangling massive data sets yourself, or maybe you're just curious about clever ways to handle data efficiently.
Yeah, HyperLogLog is, it's a pretty powerful tool. It lets you get a really good estimate of the uniqueness in your data.
And crucially, without needing a ridiculous amount of computer memory or processing power.
Exactly. Much, much less than traditional ways.
Okay, so our mission for this deep dive is pretty clear then. We want to get our heads around HyperLogLog. What is it, really? Why is it useful?
And get the basic idea, the intuition of how it works its magic, all based on the stuff we've been reading up on.
Cool. So let's maybe start with why those traditional ways are such a problem again. You mentioned memory.
Right. Think about using, say, a set data structure or maybe a hash map. To count unique things, you fundamentally have to store every unique thing you see, at least temporarily.
So if you see user A, you note it down. If you see user B, you note it down. If user A comes back, you check your list and say, already seen them.
Precisely. Now imagine doing that for, say, billions of unique website visitors over a month, or billions of distinct IP addresses hitting your servers.
The list itself just gets enormous.
Astronomical. The memory you'd need just to hold that list becomes the bottleneck. It's just not feasible for truly large scales.
It's like needing a whole warehouse just for the guest list at a giant party. And that's where HyperLogLog comes in, being all clever.
Yeah, it gives you an estimate of that guest list size, the cardinality, but it does it with really high accuracy. We're talking typically around 98% accurate.
98%. That's pretty good for an estimate.
It's very good for most practical purposes. And the kicker is the memory it uses. It's tiny. And it's fixed.
Fixed? What do you mean fixed?
I mean, whether you're counting 1,000 unique items or 10 billion unique items, it uses roughly the same, very small amount of memory. Maybe around 1.5 kilobytes.
Wait, 1.5 kilobytes for potentially billions of items?
Yep, that's the magic. That small fixed memory footprint is what makes it so amazing for big data. You can suddenly estimate unique counts on scales that were just impossible before.
Okay. My brain is slightly fizzing now. How does it do that with so little memory? Let's get into how it works.
Right. Let's break it down. It sounds complicated, but the core ideas are actually quite intuitive, surprisingly. The first step is hashing.
Hashing. Okay, I've heard of that. It sort of scrambles the input data, right?
Kind of, yeah. You take each item, like a user ID or an IT address, whatever you're counting, and you feed it into a hash function. This function turns it into a string of bits, a binary number that looks pretty random.
Like a unique fingerprint almost.
A fingerprint, yeah, that's a good way to think about it. And crucially, the same input always gives the exact same hash output.
So if the same user visits twice, they get the same hash fingerprint both times.
Exactly. So the hashing step itself automatically handles duplicates in a way. You don't need to check against a list. If two items are identical, their hashes will be identical.
Got it. So every unique item gets turned into this binary fingerprint. What happens next?
Okay, so you have this binary string, this hash. The next step is to conceptually split it into two parts.
Two parts.
Yeah. The first few bits, let's say the first P bits, are used to decide which bucket this hash belongs to. Think of it like sorting mail.
Buckets. Like containers.
Exactly. Virtual containers or registers. If you use, say, P equals 4 bits, then you have 2 to the power of 4.
16.
16 possible combinations for those first 4 bits, so you have 16 buckets. Those first few bits of the hash basically tell you which of the 16 buckets to put this item's information into.
Okay, so the start of the hash assigns it to a bucket, like sorting users into 16 groups based on their hash prefix. What about the rest of the hash bits?
That's where the really clever bit comes in. For the remaining bits of the hash string, you look for a specific pattern. The number of leading zeros.
Leading zeros, like how many zeros are there right at the beginning of that second part of the hash?
Exactly. You count the consecutive zeros starting from the left. Maybe it's 001, so that's one leading zero. Maybe it's 0001, that's three leading zeros. Maybe it's just one, that's zero leading zeros.
Okay, so you calculate this count of leading zeros. Then what?
For each of those 16 buckets we talked about, you only keep track of one number. The maximum number of leading zeros you've seen so far for any hash that landed in that specific bucket.
Hold on. So bucket number 5, for example, might see hashes with one leading zero, then three leading zeros, then two leading zeros. It only remembers the three.
Precisely. It just keeps updating its record to the highest count it's encountered for that bucket. So each of the 16 buckets ends up holding just one number, its maximum observed run of leading zeros.
Wow. So instead of storing every unique item, you're just storing 16 small numbers.
Essentially, yes, although in practice, you typically use more buckets, maybe thousands, for better accuracy. But the principle is the same. You store one maximum leading zero count per bucket. That's why the memory usage is so low and fixed. It just depends on the number of buckets, not the number of items you feed in.
That's incredibly efficient.
Yeah.
But how do those 16 numbers, the max leading zeros, tell you how many unique items you saw in total? That seems like a leap.
It does seem like a leap, but there's some neat probability behind it. Think about flipping a coin, getting heads. Let's say 0 is heads and 1 is tails in our hash analogy.
Okay, flipping a coin.
Getting one head then a tail? It's pretty common, right? Probability is 1 in 4 if you consider two flips. Getting two heads then a tail, 001. Less common, 1 in 8.
3 heads, then a tail.
Yeah.
001. Even less common, 1 in 16.
Exactly. Seeing a long run of leading zeros, like flipping many heads in a row before you get that first tail, is a rare event. The longer the run, the rarer it is.
Right. You wouldn't expect to flip 10 heads in a row very often.
Precisely. So in HyperLogLog, if you start seeing hashes that produce long runs of leading zeros, even if it's just the maximum seen in a bucket, it suggests something.
What does it suggest?
It suggests you've probably processed a lot of unique items. You needed many attempts, many unique hashes to stumble upon one that, just by chance, started with such a long, improbable run of zeros.
So the rarity is the key. If you see lots of these rare long runs across your different buckets, it's evidence that you must have thrown a lot of unique darts hashes at the board to get those lucky hits.
That's the core intuition. The distribution of those maximum leading zero counts across all the buckets gives you a probabilistic clue about the total number of unique hashes you've processed.
And then there's a formula.
Yeah, then there's a mathematical formula. It involves taking a type of average, actually a harmonic mean, of values derived from those maximum zero counts, and doing some adjustments that translates those counts into the final estimate of the total unique items. We don't need to dive deep into the exact math, but that's the gist.
Okay, wow. So the hashing randomizes things, the buckets distribute the work, and the leading zeros act like a probabilistic ruler based on rarity.
You got it. Those visual analogies help too, right? Hashing turns users into random IDs. Buckets are like maybe 16 coin jars. Leading zeros are like counting coin flips until heads. And the final guess is based on how rare those results were across the jars.
That makes a lot more sense now. It's clever. So where is this actually, used in the wild?
Oh, it's used all over the place, often behind the scenes. We mentioned counting unique website visitors. That's a classic.
Yeah.
Counting unique IP addresses in network traffic logs for security, or just understanding traffic patterns. That's another big one.
Makes sense.
And lots of big name data platforms use it. Think about Redis.
The caching system.
Yeah, it has HyperLogLog commands built in for counting uniques. PostgreSQL often has extensions available for it. Google BigQuery uses HyperLogLog algorithms. Apache Druid, a popular real-time analytics database, relies on it too.
So it's not some obscure academic thing. It's actually powering parts of the infrastructure many people use every day.
Absolutely. It's a workhorse for estimating cardinality efficiently in the world of big data analytics. For many of these systems, getting that 98% accurate estimate fast and with low memory is way more valuable than spending ages trying to get a 100% exact count.
Yeah, often an extremely precise estimate is perfectly fine for spotting trends or making decisions.
Exactly. It's often good enough and vastly cheaper computationally.
Okay, so let's just quickly recap the big wins for HyperLogLog. Number 1, highly accurate estimates of unique counts.
Right, typically around 98% or even better, depending on the configuration.
Number 2, incredibly small and fixed memory usage, like 1.5 KB, regardless of whether you count thousands or billions of items.
That's the killer feature for scalability, yeah.
Which makes it perfect for big data, where memory is often a huge constraint.
Absolutely. And it's worth remembering, this is just one example of something called probabilistic data structures.
So there are others like it, doing different clever estimation tricks.
Yeah, there's a whole field. Things like Bloom filters, count-min sketch. They all trade a tiny bit of certainty for massive gains in efficiency, especially speed and memory. It's a really smart way to handle problems that seem impossible at scale otherwise.
It's kind of an aha moment, isn't it? Seeing how a bit of probability and clever math can solve these huge computational headaches.
It really is. It shows incredible ingenuity in computer science, thinking outside the box of perfect, exact answers.
It really does. And it makes you think, doesn't it? Like how many times, maybe even in everyday life, would knowing an approximate count of unique things quickly be super useful? Even if getting the exact number is just too hard or too slow? Where else could these good enough estimation techniques be hiding? Or where could they be applied? Something to mull over.
Definitely food for thought. And if you found this interesting, there's more out there. You could look into those other probabilistic structures we mentioned, or even dig into the specific math behind HLL's accuracy guarantees.
Yeah, there's always more layers to peel back if you're curious.